Okay, so if you heard me say this earlier, great. If not, here it is. This today is the end of Chemistry 1, new material. So crazy. So, end of new material for chapter 8 and 9. Review day on Wednesday or practice day, whatever you want to call it. Friday's the exam. Then you have a week of Thanksgiving break. Then we come back and have a week of review for the final. And then the final's just the next week after that. It's like Tuesday, Wednesday, Thursday, I think. It happens really fast after Thanksgiving. There are certain years where there's like 2 weeks before finals after we get back, but I like it like this. And then if you're a freshman, you get to experience the glory of the month-long winter break. It's so nice. I always end up painting some room in my house because it's like, what am I going to do with myself? It's great. I always forget that it's coming too. So look forward to all of this. If you are on the cusp of not passing the class, that might be a good reason to study all week during Thanksgiving break. Otherwise, you can just give yourself the week off. You're going to have like a good 10 days, probably 9 or 10 days to study for the final once you get back. So I would take the break if you feel like you can. Okay, so we're going to wrap up our discussion. We have a little bit left to do about electron configurations. Then we're going to talk about atomic size, which is super cool because it ties back into this idea of Z effective. And then we're also going to talk about ionization energy. Now, I had said, or at least I marked it off on the notes, that we were skipping 1 or 2 things on ionization energy. We're not, because I realized that we are not talking about electron affinity. So if you're looking in the textbook, sadly, I'm not going to talk about electron affinity. We'll talk about a version of it at the beginning of second semester. Okay, so one of the cool things about electron configurations, and really this is just where, orbital diagrams, electron configurations, however you want to think about it, the placement of the electrons in the orbitals corresponds to their reactivity, because that's what dictates chemical reactivity, is where the valence electrons are, their energy. And when we look down a particular column, we know that Mendeleev organized the periodic table according to placing things that had similar chemical reactivity together. But now we have an explanation that corresponds to where the electrons are. So if we look at lithium and sodium, they do differ by principal energy level. Okay, so this is lithium, and then sodium looks like this. Okay, so they differ by what their valence shell is. In the case of lithium, the valence electrons are at n equals 2, and in sodium, the valence electrons are at n equals 3, but they both have 1 electron in their outermost s orbital. Okay, and that's true of all the ones further than that too. 1 electron in their outermost s orbital. So they do have some differences because of what that principal energy level is, but it's all very similar because of that 1 electron in the s orbital. So one way that we see this is in the charges that they form when they form ionic compounds. So if you look at the next page, we have that reminder of what those likely charges are for things when they form ionic compounds. So like we know that the metals lose electrons, the nonmetals gain electrons, and it is consistent based on their column in the periodic table. That isn't true once we get into the into the transition metals because of the d orbitals, which is really why we don't consider them main group elements, because they don't follow the same behavior as we would expect. Okay, But if you look at the first column, those always tend to lose one electron when they form an ionic compound. So that is one of the simplest things we can say about their chemical reactivity. When they are exposed to a nonmetal, they will lose one electron. There's obviously other things we've talked about, like the behavior of the alkali metals in water. That's where they're reacting with the oxygen, and then the hydrogen gas is given off. Each one of them do that. And the reason why they all act in that same way is because their electrons are in that same orbital, albeit in different principal energy levels, but in an s orbital, and there's only one of them in that s orbital. Okay? Same thing with the halogens. So if we switch this to fluorine and chlorine, now they look like this and that. Okay? So again, only differing by their principal energy level, but they both have 7 valence electrons. They're in, and that's an important thing to notice. Remember, this is what dictates valence electrons too. 1 valence electron, 2, 3, 4, 5, 6, 7. Okay? Once we get to 8, the noble gases, then we've completely filled the s and p orbitals, and that's why the next row is now a new valence shell. Okay, so when you look at this, not only do they have 7 valence electrons, but if you'll notice, there's one open place that, if compared to a metal, is relatively low in energy. And we'll, again, talk about this more as we talk about size today. But there's one open place where an electron could be added to. Okay? So that is why we get the halogens when they form an ionic compound, when they react with a metal, why they're going to gain 1 electron. Why don't they gain 2? Because the next place that they would have to go if they were to gain another one is way up higher in energy than what exists already. Okay? So we're showing both as to why they form the charges that they do, and also when we're talking about going down a column, why all of those have similar properties, both in the charges that they form and in just general chemical reactivity. The bonding in covalent bonding, which again we'll get into at the beginning of Chem 2. I'm talking like you're all going to be there. Don't worry, my feelings won't be hurt if you're not, but it is some pretty good stuff. So when we get into covalent bonding, we're going to end up seeing why these guys end up forming diatomic molecules, like F and another F. They're going to end up forming diatomic molecules, and they're going to be a single bond. So like F2 looks a lot like Cl2, which looks a lot like Br2. Whereas when we look at oxygen, maybe even sulfur, we're going to see sulfur isn't technically a diatomic, but if it were to bond with itself, it would form double bonds. That should be an S. Okay? If we looked at nitrogen and phosphorus, those would form triple bonds. Okay? So there is this, why do I keep doing that? There is this inherent similarity between the bonding that exists within a given family. That's why we call them families, the columns, because they have similar properties, similar genetics or something. My son asked me the other day, he was like, why is your hair like white and mine is like brown? And I was all, well, look at Dad's hair. His is like really brown, right? Like, you're not just from me. Like, why is that so shocking? He's 9. He's not like 2. Anyway. All right. So that's pretty much the end of talking about electron configure. Oh, no, it's not. I should scroll before I speak. Okay, one more thing we need to hit on, and I noticed 2 errors on this in the other class. Change that helium to neon, and then change neon to argon. Unless maybe I was meaning something different when I said that. No, that makes sense. Okay, so this should probably be relatively self-explanatory. But if you're talking about the electron configurations of an ion, you have to either like add or remove electrons correspondingly. So if you have aluminum, this is its electron configuration. If you say aluminum 3+, you got to remove 3 electrons. They have to be the highest energy electrons. So 1, 2, 3, okay? So you eliminate those 3 electrons. If you're talking about gaining electrons, you have to add them, again, to the highest energy orbital. So S to S2 minus, we just fill out that last, those last 2p available spots in the p orbitals, okay? So instead of 4p, it becomes 6. It's also probably important to notice that this now corresponds to the same electron configuration, we call it isoelectronic, with noble gases. So all of the elements, and this is not some magical thing that they're trying to be happy and be like the noble gases, it's just that they have the capacity to fill in their valence shell in order to fill the S and the P. So they will eventually look like noble gases because either they fill in that shell completely, or in the case of aluminum, they eliminate their valence shell and then they look like the noble gas that preceded them. So if you look where aluminum is, 3rd row, when it loses those 3 electrons, it's now going to look like neon does, or have its 2s and 2p completely filled. And when you look at S2 minus, it fills in its shell, so it goes to the next noble gas, or argon, and fills up its 3s and 3p. Okay, so I'm, pretty sure you'll have homework questions that are like, oh, what's the electron configuration of sodium? What's the electron configuration of sodium plus? Like, just make sure that you realize those are different because they're gaining or losing electrons. Now I'm done with talking about electron configuration. Okay, any clarifications on that before we move on to size? Okay. All right, your book I do not think has a picture like this, or if it does, it's not as good as this one. So this is my preferred way to remember or think about the size of the atoms. And obviously on the test, you're going to have a periodic table. And what I would recommend, just like I do with when we talked about charges, I said rip it off and write down +1, +2, +3, or write down the number of valence electrons, or whatever. I want you to do the same thing with size. So when you look at this, you can pretty quickly see that there is a trend in the size based on the position in the periodic table. Now, when we say size of an atom, that's defined by its outermost, where its outermost shell is. So where the valence shell extends to is going to define its size. So before we even talk about the Y, recognize that these guys in this corner are relatively small compared to the ones over here. Okay, and even more specifically, we can look within a given row and within a given column and see that the size decreases as we go, like increasing atomic number from, left to right, the size decreases. As we go down the periodic table, also increasing in atomic number, although, jumping quite a bit, the size actually increases. So you certainly cannot rely on, oh, it has more protons, it must be bigger, or it has more protons and more electrons, it must be bigger. It doesn't work that way. Okay, so that is the basic trend. Now we need to talk about why that happens. And then finally, we'll tie in ionization energy, connecting it back to the size. Okay, so we talked about Z effective quite a bit. I don't know why the book introduces it so early. Maybe next semester I'll just leave it behind until we get to this point. But I guess in some respects it might have been useful for the electron configuration conversation. Okay, so we're going to go back to the idea of Z effective and use it to explain this size thing. Okay, so we've got lithium drawn up there. I'll probably add fluorine to it in a second. Now I had have fluorine here. Maybe I'll leave it there. And we'll draw lithium as well. Just, like I said, I like to look at orbital diagrams with you guys a lot more than just the electron configurations, especially this early on. Okay. All right. So lithium has its 3 protons. It has the 1 valence electron, and then it has 2 core electrons. And remember, those core electrons, because they're physically between the valence electron and the nucleus, they're going to have way more of an effect than just simple electron repulsion. So when we talk about valence electrons like these guys, these 7 valence electrons in fluorine, when I talk about those, I talk about them as just electron repulsion, okay? These guys are next to each other. They don't want to be super close, but they want to be close to the nucleus. When we talk about core electrons, it's like an extreme electron repulsion issue, and so we give it a different name. We call it shielding, okay? Because it is physically kind of blocking and also electromagnetic repulsion-ing the positive charge from those valence electrons, okay? So that's the idea of how we incorporate core electrons. So we can do this equation. It gives us a rough idea, and we can say that lithium had 3 positive charge units, that valence electron should feel that positive charge. It should feel the attractive force there. However, it has 2 core electrons that are kind of blocking that positive charge. So it only actually, the valence electron only actually feels about 1 unit of attraction, okay? That's fine. That's still an attractive force. It's still holding the electron on there. Sometimes people talk about it like lithium wants to lose that electron. No, they are attracted to each other. This electron and this nucleus are attracted to each other. It's not going to just like lose that electron for no good reason. It's going to take some energy if we want to remove that electron. It's just that it's not as attracted as something like fluorine. Okay? So fluorine, if you look at the periodic table, we're talking about the same row here. So they're in the same valence shell. They're still in N equals 2, which means if they have the same valence shell, or remember, if they're in the same row, that means the same thing, they are going to have the same number of core electrons. Because even though fluorine has 7 valence electrons, every one of those has been added to N equals 2, and the core electrons hasn't changed. The only time core electrons change is when you move from a noble gas to the next row. Now you've added another layer of core electrons. Okay? So between lithium and fluorine, core electrons has been consistent, and the number of protons is what's really changed. So in red here, for fluorine, the Z is now, sorry, not 7, 9. Okay? And the core electrons is still 2. We still have the same number of shielding. There is some additional repulsion on the periphery because it's not just 1 valence electron. It's not enough to outweigh the attractive force, though, that comes from having all those additional protons. Okay, so the Z effective, or the attractive force that each of these valence electron feels, is 7 times that the lithium's valence electron feels. Okay, so at this point, it shouldn't be super crazy to recognize that fluorine is smaller, because the size is dictated by where the electrons are. And if they are 7 times as attracted as the electron in lithium, they're going to squish in as tight as they can until they start feeling too much repulsion from each other. So this is the whole thing in chemistry, is you're trying to maximize that attraction, so they squish in close to the nucleus until it starts feeling too tight with their neighboring electrons, and then maybe they back off a little bit. Okay? So fluorine's going to end up significantly smaller than lithium. Let's see, do I have numbers there? I do. Okay, so it's not quite half the size. 129 picometers for lithium, 67 for fluorine. Okay, so there's a big change in size there, even though you're in the same principal energy level. You're still at N equals 2. That's why when I draw these, I try to like be careful as to how I draw the energy levels, because what happens is that you actually pull the energy levels in tighter. So the 2s in fluorine is not at the same energy level as the 2s in lithium. This 2s orbital is actually higher in energy than it is here in fluorine. In fact, it's higher in energy than the 2p is. Okay? So when we pull things in tighter, that is a result of the attractive force, but recognize that also lowers the potential energy of those electrons. I'm sure I have that written down. Let me highlight it. I'm trying to find the wording I want. I might have to write it down myself. This is the wording to explain why it happens. I don't think I have the actual potential energy thing in there, so I will rewrite it. So we'll put it up here. Smaller size means that the electrons will be at a lower potential energy. Those valence electrons, because they're closer to the nucleus, they're going to be at a lower potential energy. Okay, so I'm going to jump ahead just for a second. We'll come back to size and size of ions and stuff. But since we're here and we just said that the electrons in fluorine are going to be at a lower potential energy, what do you think happens when I stick lithium and fluorine, neutral lithium, neutral fluorine together? And they look like this. Okay? This electron, so is not about... People talk about the atoms being happy. I really think if we're going to talk about happiness here, we should talk about the electrons being happy. But this electron sees an available spot that is lower in potential energy. So of course it's going to leave lithium and be attracted to fluorine because it can be at a lower potential energy. It can be closer to the nucleus. It can be closer to a very highly positively charged nucleus. And so it is going to move over there, and this guy is now going to become lithium plus, and that's going to become F minus. Okay, this is why ionic bonding happens. So from the beginning, we've told you, oh, metals tend to lose electrons. That is because they are bigger, because they have fewer protons compared to the amount of shielding that they have. And so the electrons are just not as attracted to them as they are to a nonmetal. Nonmetals tend to gain those electrons because they're small, they have open available spaces that are low in potential energy. This should also make sense why noble gases don't participate in ionic bonding. They don't tend to gain electrons because even though they're small, they don't have an available space, right? This would be like what neon would look like. If it wanted to gain an electron, the electron would have to go up there. That's not going to happen, okay? So when we talk about noble gases being like happy because their valence shell is filled, they're not happy. They just don't have anywhere to gain electrons to that's low in energy. Also, they're not going to give up any electrons because they are relatively small and have a good hold on those electrons. Okay, since we've got this up, let's talk about the size of the ions. We'll come back to that in a second. Okay, how does the size of the atom change once it's either gained or lost electrons? Okay, we just did this to lithium. We had an electron here. So like the size of lithium to start was defined by the 2s, right? It just lost that electron, meaning it lost the entire valence shell, right? There's no more electrons in N equals 2. So now lithium plus's size is defined by the 1s. So when things lose electrons, they tend to lose their entire valence shell. For lithium, that was just 1. For beryllium, it would be 2. For boron, it would be 3. But they lose the entire valence shell, and that's why they get so much smaller, is because they have now completely lost an entire shell. So the red is showing the ions and the gray is showing the neutral atoms. You can see they get smaller from gray to red every time. You can also notice though that like the red ones, they still increase in size as you go down the periodic table. They still decrease in size as you go across. So there's still that same trend as long as you're comparing ion to ion. Gaining electrons is a little bit harder to understand, but actually a little bit more interesting. So fluorine's electrons were defined by N equals 2, right, where that last valence shell was out, and then it gains an electron. Okay, we're looking at the data. It's telling us that fluorine, oh my gosh, it almost doubles in size, 72 to 136. That doesn't make a whole lot of sense because we're like, well, it didn't gain a shell. It's not like it jumped up to N equals 3, so what's going on? Okay, so remember I talked about all those little electrons are pulled in tight to fluorine, right? And they're like trying to get as close to the nucleus as possible. They're probably so close you can think of them as like 7 people standing shoulder to shoulder, and they can't move in any further, okay? We bring along another electron and try to squeeze it in there. The only way it's going to be able to get in is if everybody takes a little bit of a step backwards, and now they can add another person in there. Okay? So in that taking a step backwards, that's why the atom gets bigger. It always surprises me that it gets that much bigger. Like, really? Doubles in size just to accommodate one more electron? That's pretty crazy. And you see that with all of the anions, okay? So O2 minus adds 2 electrons. It also, has a significant jump in size. And as you look at the green ones, they still are increasing going down the periodic table. They're still decreasing going across the periodic table. Selenium's 198. Bromine's only 195. It's not quite as dramatic of a decrease as we saw with the atoms themselves. I guess the atoms themselves, the decrease isn't that dramatic. There's an interesting thing that happens when you get to this far into the periodic table is that they're already so squished in there, the electrons, that even that additional proton can't make a huge difference in the size. That going across a row is most dramatic when you go from, the far side on the left to the right. Okay. So let's take a pause and let you guys take a application thing. So we're gonna do this practice problem. Although as I was looking through it, I'm pretty sure I intended these to be 2+. I think that's what I came up with. Let's go with that and see if that's what I want. Okay, so as you're looking through these examples, I want you to actually predict what they are. If you have the time before I start talking again, it would be a good idea to think about why that happens. So we talked about these two things, why cations and anions change. But really when you're looking at any, comparing two things and their size, you can always bring it back to these factors. So does the principal energy change, right? The shell. Does the number of protons change? Because if we're in a given shell, but the protons is changing, that's going to suck the electrons in more. Or is there any additional electron repulsion that might account for a difference? okay? Maybe I give you a question where I tell you the sizes and then I say, tell me, what best explains this change in size. All right, so go ahead and take a few minutes to practice these few practice problems. So if you're getting stuck, I went ahead and didn't put the answers up yet, but I put the explanation of like how you choose between each. Okay, I'm gonna write the answers here. I feel like I should just say like circle the smaller one. That would be easier. Okay, so I think it's really useful to go back to these three potential explanations when you're thinking through this. Or if you just want to think of, like, we talked about trends for neutral atoms. We talked about how does the size compare cation versus neutral or anion versus neutral. The only one where that gets a little bit difficult is when we compare two different ions. Now, Mg2 plus and Cl minus shouldn't be that difficult, because if you look, they're initially on the same shell, but Mg2 plus loses 2 electrons, and so now it's at N equals 2. So it doesn't matter that they're both ions, you can just rely on the fact that the shell is less for Mg2 plus. The most interesting one to me is the Mg2 plus F minus, okay? Because they're on different shells initially, but Mg2 plus, so initially you would probably say, oh, magnesium is bigger, like if we're talking about the neutral atoms. But magnesium lost 2 electrons, so now it's at N equals 2. So its electron configuration is going to be 1s2, 2s2, 2p6, whereas F minus has gained 1 electron and is also 1s2, 2s2, 2p6. Okay, so they have the same electron configuration. They're isoelectronic and isoelectronic with neon. So the shell is the same. The electron repulsion has to be the same because they have the same number of electrons. So the only thing that differs here is the number of protons. So magnesium has more protons, and therefore everything will be sucked in tighter. And this is like completely opposite of what we would expect in their neutral forms, okay? All right, so your homework will definitely have some of those examples for you guys to go through as well. This is me waiting for questions before I move on. Okay, so ionization energy. We hinted at this when we talked about lithium losing an electron to fluorine, okay? We said a lithium is bigger, its electron then must be higher in potential energy, and so the electron would be much more likely to want to go to fluorine that's smaller, and therefore it would be at a lower potential energy. So if you look at this chart, well, first of all, we need to say what the definition of ionization energy is. It's the energy required, because you are going to have to provide some energy to remove an electron from an atom. Your book will talk about other ionization energies, second and third ionization energy. We're just talking about first ionization energy, which is just the energy to remove that first electron. Okay? So when we look at these values, low ionization energy values means it's easy to remove an electron. High ionization energy means it's difficult to remove an electron. And these charts, this is what your book likes to present it as. Maybe this picture is from the book, I'm not sure. But like I said, I always like to think about it more with reference to the periodic table. So if you notice, these guys over here are the higher ionization energies. So it takes more energy to remove an electron. And these guys down here are the lower ionization energy, or easier to remove an electron. And if you notice, those correspond just exactly inversely to size. So smaller size means higher ionization energy. Larger size means lower ionization energy. Same thing if you go across a row, you're going to increase. Now there are these little blips, like you increase and then it goes down and then back up. You don't need to worry about those. If we had more time, we would talk through them because they're actually really interesting. It has to do with like when you start pairing up electrons in the p orbitals, and that added repulsion kind of like counteracts some of this. but I'm not going to worry about that right now. Just know the general trend is increasing as you go across a row, just like the size decreases, so they're inverse each other. And then as you go down a column, the size increases, ionization energy decreases. So why is that the case? Bigger atom, electrons are further away from the nucleus, they're easier to remove because they're just not as tightly bound to the nucleus. Small atom, electrons are held very tightly because they're nice and close to the nucleus. It's going to be very difficult to remove them. Lithium, easy to remove the electron because it's far away. It's going to go to fluorine. Fluorine is definitely not going to give away one of its electrons. The electron doesn't have any reason for wanting to leave. It's nice and close and tight to the nucleus, strongly attracted. In fact, so much so that it will attract more electrons. And this is why ionization energy, or rather ionization energy is the explanation as to why metals tend to gain electrons, non-metals, I said that the wrong way. Metals tend to lose electrons, non-metals tend to gain them. Because non-metals are small. Why are they small? Because they have a lot of protons compared to the shielding. Why do metals lose electrons? Because they're big. Why? Because they have not very many protons compared to their shielding. Okay? It all is going to go back to this. How does the positive charge affect the size? And how does that then affect the potential energy? And as we get into Chem 2, those of you that'll be there, we'll talk about electronegativity, which is this idea that fluorine is so small, or these atoms are so small, that they're very good at attracting electrons. And that's going to have an influence not only in ionic bonding, but also in how they attract electrons in covalent bonding. I need to think about what else I have to say. It might be it. Okay, so this is all in words. Do you guys, is that annoying that I have that? Probably not, because then you don't have to write everything down. So I just say it in my own words, and I've written it in my own words, but I pull a lot of images from Pearson, but I kind of hate the words they use to describe things, so I just rewrite them. Like I said, we're not going to talk about second, third, fourth ionization energies, so you don't have to worry about a question like this. And then this is just summary of topics, pulling size and ionization energy together. Okay, so homework due tomorrow night. Ideally, you look at the practice exam before Wednesday. I realize that's a lot of stuff, homework and the practice exam. But if you've made good progress on the homework, maybe that's possible. We'll just kind of gauge what the interest level is on Wednesday, whether we do questions that you guys have, whether there's stuff that I feel like we need to practice more, or whether we just kind of use it as time for you guys to work on the practice exam. Exam on Friday, and then we'll just focus in on the final when we get back. Okay? All right. Good luck. Happy studying.